So starting from today's class, we are going to start looking at a new topic, which is the design of digital filters, and this class will primarily be motivation about that. So let's try to briefly recap all the things that we have been doing in class so far. The initial phase of the class was basically understanding the sampling theory so that we know how can we process continuous time signals in discrete domain. So for that we looked at, okay, what should a filter, how should we design our filter in the discrete domain? But those filters that we quote unquote designed were actually just ideal filters, okay? And the last few classes what we have looked at is how do we process the input of filters in a more efficient manner using the DFT, and how can we do analysis of signals using the DFT. Now in this class we want to move from those idealistic aspects of filter design to realistic aspects. So what do I mean by that? Well, for that I need to remind you that ideal filters cannot always be implemented in hardware. So an example of this is an ideal filter that you have seen many times so far in your class designing. So the example is you're given this system, an LTI system, AHN is its impulse response, and based upon all the specifications you say that the filter has to be a low pass filter. So you come up with the frequency response of the filter to be 1 between minus omega c and omega c for omega between minus pi and pi. So this is our ideal low pass filter, which we have seen many times in class. And it has a cutoff of omega c. Now on paper this is a perfectly valid filter. We know what is the impulse response of this low pass filter. The impulse response is sine omega cn over pi n, which has the sinc formulation, and n is from minus infinity to infinity. A perfectly valid filter on paper. The question is the following: how do we implement this? And the reason we are asking this question is because we know filter implementation has to do with either we can use the convolution formula or we can use some other trick which we'll come to later. But this is a filter that extends from minus infinity to infinity, and if you were to try to use the convolution formula you couldn't do that directly. If you look at the convolution formula directly, we have yn, and I can write it as m from minus infinity to infinity, ahm x of n minus m. Now since my ahm always is non-zero, this means that to compute this output for every little n, even if I want to compute my first sample y of 0, I have to compute an infinite summation, and no computer can do that. So I cannot implement this filter using the convolution formula directly. Okay. So when we talk about design of digital filters, This is what it means. Design of digital filter means how do we approximate filters that we desire so that they can be implemented in hardware. So it's not just a fact. Design here does not just mean give me the mathematical expression. Design here literally means that you can now take whatever filter you have and you can put it in a digital system and you can get an output. So a filter that we saw earlier, the ideal low-pass filter, even though it's a perfectly valid filter, from the design perspective, it's not the right filter because we cannot implement that. So let's keep on going with this formulation though. Let's keep the example of this ideal low-pass filter. And let's try to motivate what is to come in terms of design of digital filters. So we are given this filter HN, which is infinite length sine of omega Cn over pi n. How do we now get an approximation to this filter so that we can implement it in hardware? So there are two ways of doing that. There are two types of approximations that we'll try to study in this class. The first approximation is that we approximate this ideal low-pass filter with a finite impulse response filter. Or FIR, which is the term that is often used, filter. Okay. That is one of the techniques for designing a filter. You start with something that is ideal, that cannot be implemented, and using very systematic approaches, you reduce it to a finite impulse response filter, or what's commonly called an FIR filter. So let's first formally define what is an FIR filter. Okay. An FIR filter, as the term says, finite impulse response. It is defined in terms of the impulse response of the filter. Okay. And as the term says, if the impulse response of your filter becomes 0 after a certain range and stays 0, then that's a finite impulse response filter. So formally, a filter whose impulse response is 0 for all n less than capital N1 and n greater than capital N2. So effectively, after a certain range, it can be 0 within that range, but after a certain range, it stays 0. So a filter like, for example, I'm going to draw the envelope. It is a discrete time filter. Don't get me wrong, but I'm going to draw the envelope here. A filter like this. So these are my the impulse response. And it stays 0 afterward. So this is my N1 and this is my N2. Okay. If I have a filter with an impulse response like this, it's an FIR filter. Even a filter like this, which basically becomes 0 for a range, then becomes non-zero, and then becomes 0 and stays 0. A filter like this is also an FIR filter because it stays 0 afterward. Now the filter that we saw here, this is not an FIR filter because it is non-zero for all values of n. So FIR finite here does not correspond to the magnitude of the filter. Finite here corresponds to the length of the filter. Okay? A finite impulse response filter is defined by a finite numbers or a finite collection of numbers. So if the filter is non-zero from, let's say, n equal to 0 to n equal to 100, that's an FIR filter of length 101. Okay? So typically we say that we talk about length n FIR filters, which is saying it is non-zero for a total of capital N indices. Now, in our calculations, we are actually most interested in causal FIR filters. So a causal filter is something that basically does not produce an output. A causal filter, a causal system, they are the same term. A system whose output does not depend upon future inputs is a causal filter or a causal system. For example, if my Hn was equal to, let's say, delta of n plus 1. So what is the impulse response? What is the technical definition of impulse response? It is the output of my system, of my filter, in response to an impulse applied at n equal to 0. Right? So I have a filter which is generating an output at n equal to minus 1 for an input that was applied at n equal to 0. So I have this system, my yn, my input is xn equal to delta n, which is an impulse at n equal to 0. But I am saying my impulse response is an impulse at n equal to minus 1. What is wrong with this picture? What is wrong is that this is a non-causal system. This system is anticipating what's going to happen at n equal to 0. The input is going to be applied at n equal to 0, but the output has been generated at n equal to minus 1. So these are non-realistic systems or filters. No realistic system in the world will produce an output before the input is applied. So these kinds of systems this is a non-causal filter. Okay. The technical definition of a causal filter is that output does not depend on future inputs. That's the technical definition, and that is irrespective of whether you have an FIR filter or some other filter. Okay? Now, the test for a causal filter is very simple. The test for a causal filter is if your impulse response is non-zero for n less than 0. Because keep in mind again, the definition of impulse response is what is the output when you apply an impulse at time n equal to 0. So you should not get an output for n less than 0. Otherwise, it is a non-causal filter or system. So the test for causal filter is if Hn equal to 0 for all n less than 0, then this is a causal LTI system. or causal filter. And of course, everything in the real world is causal. We don't have this magic of figuring out what the input will be. So if we go by that, then causal FIR filters are defined as filters you have Hn equal to 0 for all n less than 0 and n greater than n minus 1. And we call these length n FIR filters. So whenever we are talking about design of digital filters using FIR filters, we'll stick with causal FIR filters. If I just say I'm talking about length 128 filter, the automatic assumption is it's a filter that goes from Hn equal to 0 to n equal to 127. Okay. So those are the specific definitions of FIR filters, causal FIR filters. Let's now go back to the question of why is an FIR filter, and specifically a causal FIR filter, implementable? So let's see what happens if you have a causal FIR filter, which will help us address why an FIR filter can be implemented. So go back to our definition of convolution formula, which is m from minus infinity to infinity, h of m, x of n minus m. But since now my h is FIR, this means that this is 0 for all m less than 0 and m greater than n minus 1. So I can just have my summation from m equal to 0 to n minus 1 hm x of n minus m. Okay. So what is the point of this? That now if you look at the convolution formula for each output yn, for each index n, the previous example that I gave you, for each little n you had to compute an infinite summation, which you couldn't do. But in the case of an FIR filter, for each n you have to compute a total of n terms, right? So you have a total of n terms that need to be multiplied and added. That is totally doable. If, for example, your FIR filter was 1024 length, which is a really large filter, typically you don't go that high. But even if it was 1024, that's just 1024 multiplications and 1023 additions for each little n. You can do that in hardware. Okay? So one way of designing implementable filters is you start with a non-ideal filter, and through systematic operations you reduce it down to an FIR filter. Once you have the FIR filter, you can directly use the convolution formula. Okay. The other approach of designing implementable filters is approximating a non-implementable filter, an ideal filter, by an IIR filter, or what's known as an infinite impulse response filter, that can be represented using constant coefficient difference equations. So approximate an ideal filter by an infinite impulse response filter that can be described by a constant coefficient difference equation. So what is the meaning of infinite impulse response filter? As the name implies, it's just the opposite of the finite impulse response. Infinite impulse response, or IIR filter, is simply a filter whose impulse response either in the negative infinity direction or the positive infinity direction, it just keeps on going. It doesn't become zero and stay zero. It can become zero occasionally in middle, but it doesn't stay zero. Okay? A simple way of just saying is if something is not FIR, then it's an IIR filter. So the filter that we saw earlier, sine of omega Cn over pi n, this is actually an IIR filter because it is not FIR. It doesn't stay zero. It keeps on going in the infinite direction and minus infinity too. But this is an IIR filter. Okay. So in general, I could have said that any filter which is an IIR filter may or may not be implementable. Right? So if you get a filter which is an IIR filter and you don't see it how to implement that, the key there is to make it implementable, you have to express the input-output relationship of the infinite impulse response filter through a constant coefficient difference equation. So to implement an IIR filter, we must be able to express the input-output. So constant coefficient difference equation, I'm going to call it CCDE. The input-output relation in terms of a constant coefficient difference equation. Now, just like the FIR filters, we are only going to be interested in causal IIR filters, which are defined as the same way. Causal filter is defined in the same way regardless of whether you have FIR or IIR, that Hn is equal to 0 for all n less than 0. Okay. In that case, an IIR filter basically becomes a causal IIR filter is that starts at 0 or some point after 0, but keeps on going till infinity. For example, Hn equal to 0.5 n un, where un is the unit step. This is a causal IIR filter. Once again, this filter never becomes 0. For every little n, it has a non-zero value. It is 0 for n less than 0, but it keeps on going. So this is a causal IIR filter. This filter that we talked about earlier, this is also IIR, but it is non-causal. Okay? We could have made it causal by making it 0 for all n less than 0, but then its characteristics will change, and it will still not be implementable per se. Okay. So you are given these two filters. This is one example. This is the other example. The question is, they are both IIR. How do we implement them? Now, we can't implement them using the convolution sum because of the argument we made earlier that the sum is going to involve infinite terms for each little n output. But if we can turn the input-output relationship in terms of a constant coefficient difference equation, then it turns out that actually one of these filters can be implemented, not using the convolution formula, but it can be implemented. So let's take a look at how can you implement this IIR filter, because this indeed can be turned into a constant coefficient difference equation. Okay? So I will describe it in the reverse direction. I will argue that a system whose input-output relationship is given by the following form. So here is an example that if yn equals to xn plus 0.5 y of n minus 1, then this equation describes this filter that I wrote above. Okay. Now, this is a constant coefficient difference equation because the coefficients next to all the terms are constant. Right? These are constant coefficients. And difference equation, you have yn minus 1, xn minus 1, and so forth. Right. So, if you have to find out what is the impulse response of this filter for a difference equation, and this is where we go back to our linear systems knowledge, we will go back to our Z transform that you did in the linear systems. Okay. So if you want to find out the impulse response of this, what do? We take the Z transform of the left-hand side and the right-hand side. So let's call the Z transform of yn as y of z and xn as x of z. Okay. Now, there is a very important property of the Z transform that you have to recall. If you have forgotten, you should go and revisit those properties. But if you have shift in time, what does that mean in terms of the Z transform? So the time shifting property is if you are given, for example, y of n minus n naught, in Z transform that is simply equal to z to the minus n naught y of z. Okay. So let's take the Z transform of this difference equation. You get y of z equal to x of z plus 0.5 z to the minus 1 y of z. Okay. Now, to get the impulse response, you want to get the transfer function. So you want to get h of z, which is given by y of z over x of z. So convolution in time is multiplication in frequency, and if you do the division, you get h of z. So we want to do y of z over x of z, so we get y of z. I bring this term here, and I'm sure you have seen that many times in your linear systems class. I just take this common, I get y of z, 1 minus 0.5 z inverse equal to x of z, which means that y of z over x of z is equal to, which is h of z, 1 over 1 minus 0.5 z inverse. Okay. Now there is also the region of convergence involved with this. In the Z transform domain, we always have to talk about the region of convergence. So there are two regions of convergence that can exist for this h of z. One region of convergence could be that absolute value of z is greater than 0.5. The other one is z less than 0.5. Okay. We are going to work with this one because that gives us causal systems. Okay. So if I assume that I have h of z equal to 1 minus 0.5 z inverse with an ROC of absolute value of z greater than 0.5, then what is the impulse response? For that, we have to take the inverse z transform. And if you take the inverse z transform of this, it is 0.5 to the n un. So what we see is that the impulse response of this constant coefficient difference equation, or a system, if a system is described by this, then it has this IIR impulse response. But even though this is an IIR filter, we can implement this kind of a system very easily in hardware. How can we implement that in hardware? We just have to read this difference equation. What is the difference equation saying? Yn, which is my current output, the output at time n, equals xn, the current input, plus 0.5 times y of n minus 1. What is y of n minus 1? The output in the previous time step. Okay. So what do I have to do to implement this filter? All I do is, in hardware, I save my sample of the previous output. And every time a new input comes in, I simply add that to the previous output with a factor of 0.5, and I have my filter implemented. In IIR filter, I'm not going to use the convolution formula. What I'm going to use is turn it into a difference equation, and then I can easily implement it. So going back, if I have y of n equal to x of n plus 0.5 y of n minus 1, what this formula is saying is that every time in your hardware an xn comes in, you basically add that to the previous sample 0.5 y of n minus 1, and that is your output yn. You can draw it more formally too, but that's all the implementation is. A new sample comes in, I just add it to the previous sample, but the previous output has to be multiplied by 0.5. That's my output. If you do that, that is equivalent to implementing this IIR filter. So that is the other approach that you take if you want to approximate a filter that you want to implement in hardware. Okay? An IIR filter, but you must be able to represent it in terms of constant coefficient difference equation. So the question is there a simple way of seeing whether an IIR filter has a form that can be written in terms of a constant coefficient difference equation? And the answer once again lies in terms of Z transform. So you have to recall all the Z transform properties that you saw in linear systems, because they are going to be now used heavily in this discussion. But this one I think is not that difficult to remember. So when does an IIR filter result in a constant coefficient difference equation form? Because in the previous example, what I started with was a difference equation, and I showed it has an impulse response which is an infinite impulse response. But in general, if I just give you a filter, how do you know it's an implementable filter? And by implementable, it means that it is, even though it is IIR, it can result in a constant coefficient difference equation. And the answer lies in Z transform. We have to look at the Z transform of Hn. Okay. So to address that question, we simply look at the Z transform H of Z, and if H of Z has a rational form, which means that it is a rational function of two polynomials. In, we'll go with the standard Z inverse. Okay. So what does that mean? That my H of Z can be written as a fraction of two polynomials in Z, P of Z and let's say Q of Z, and each of these is a polynomial. So I have P0 plus P1 Z1, P0 plus Z inverse plus P2 Z to the minus 2 plus Pm Z to the minus M over Q0 plus Q1 Z inverse plus Qn Z to the minus N. Anytime your IIR filter has a Z transform that looks like this, then it automatically implies that it has a constant coefficient difference equation form. Why is that? Well, if you have forgotten, just say that y of z that is equal to h of z that is equal to y of z over x of z, right? And that is now equal to this P0 plus P1 z inverse plus Pm z to the minus m over Q0 plus Q1 z inverse plus Qn z to the minus n. So what do I do now? I simply just cross multiply and I get Q0 y of z plus Q1 z inverse y of z plus Qn z minus 1 y of z equals P0 x of z plus P1 z inverse x of z plus Pm z to the minus m x of z. And now you just remind yourselves, so now I just take the inverse z transform of this whole equation. I take the inverse z transform of left hand side and right hand side. So what is the z transform of Q0 y of z? That is simply Q0 y of n. Now remember the time shifting property. So what is the inverse z transform of z inverse y of z? That is y of n minus 1. Z powers of z inverse, they just represent time shifting. Right? So I get Q1 y of n minus 1. And I keep on going, I get Qm. So what is the inverse of, this is Qn. What is the inverse of z to the minus n y of z? That is y of n minus capital N. So I get Qn y of n minus capital N equals to P0 x of n. I do the same here. Plus P1 x of n minus 1 plus Pm x of n minus m. Okay. So indeed what this z transform being a rational function of two polynomials of z means that my input-output relationship is given by a simple difference equation. Now if I want to implement this kind of an IIR filter, what do? I simply implement this difference equation. Why? Because all this difference equation is saying is that your current output, so you can actually move all of these other terms to the right hand side. So we can move all of this to the right hand side, and I will get an equation in terms of yn. So what I'll get is that y of n equals to p0xn plus p1xn minus 1 plus pm x of n minus m. Then I bring the other things here, q1 y of n minus 1 minus qn y of n minus capital N, and then I just divide it by q0, which is just a coefficient, a scalar. So what is this equation saying? That my current output, if I want to generate an output at time n, I will generate that by adding the current input, the input at one step before, the input at the step before that, and so forth. So I need to have a buffer that contains my last m inputs and a buffer that contains my last n outputs, and I just add them all up, and that's my output. So I'm again not using the convolution formula per se. Right? I'm going to rely on this constant coefficient difference equation, and doing that solution is very simple. So anytime you are given an IIR filter, you cannot implement that in hardware, but if an IIR filter has a z transform which is a rational function of z, then you use that to write a difference equation, and then you just implement that difference equation in hardware. So since I have just relied on arbitrary variables, I'll just give a more concrete example just to help you guys out. Let's say that I was given a filter which had an impulse response given by the following. It was 1 over 1 minus 0.5 z to the minus 2 minus 0.25 z to the minus 1. Now, you use that to convert it into a difference equation. You can do it more formally the way we did it. You will get basically y of z. When I write this x of z as y of z over x, h of z as y of z over x of z. Okay. I get 1 minus 0.5 z minus 2 minus 0.25 z minus 1. If I solve that, I get y of z equals to x of z plus 0.5 z minus 2 y of z plus 0.25 z minus 1 y of z. Now I take the inverse z transform, so I get y of n equal to x of n plus 0.5 z to the minus 2, that is 2 times delay, plus 0.25 y of n minus 1. So if I have to implement that, what is it saying? That I just use my current input and I save the previous two outputs, and I simply add the previous two outputs. I multiply them by the right coefficients, and that is my new output. Okay. So again, a very simple implementation. You have to save previous two outputs. You have to multiply them with the right constant coefficients. You add with the previous one. This is the case where my output I have to save, but I don't have to save any previous inputs. And the reason for that actually ends up being that your numerator polynomial is just a constant. Okay? If I were to change my numerator polynomial to a different number, so another example could be that h of z equals to 1 plus 0.5 z inverse over the same one in the denominator. Okay. So my denominator polynomial has stayed the same, but I have changed my numerator polynomial. I'm not going to go through the entire calculation, but in that case what you get is y of n equals x of n plus 0.5 x of n minus 1. And that x of n minus, so this 1 corresponds to y of n, and this numerator polynomial 0.5 z inverse corresponds to this. Right? So numerator always corresponds to to x's, and the rest will be the same as before because we didn't change the denominator polynomial. You can do that more slowly using the h of z equal to y of z over x of z formulation. So now what this is saying is that your output, current output, you have to save the previous two outputs and you have to save the previous input. Okay? So my current output, all you do is add my current input, x of n. So you just read this equation, you add x of n and you add one previous output, previous input 0.5 x of n minus 1, and you add 0.5 y of n minus 2 plus 0.25 y of n minus 1, and that's your current input. So at every time step you just keep on saving some of the previous outputs and one previous input, and you do this calculation and you have your implementation of the filter. Again, it's an IIR filter. You cannot implement it using convolution sum. But since it has this special form, you can implement it using simple summation. So the question is, how do we exactly go from this polynomial to the difference equation that we obtained? And the trick to that is the same one that we did earlier. We just basically realize that h of z by the convolution formula for z transform is simply y of z over x of z. Okay. So we simply now cross multiply. So we get y of z is getting multiplied by 1 minus 0.5 z to the minus 2 minus 0.25 z to the minus 1 equals x of z 1 plus 0.5 z inverse. So this is the cross multiplication. Now I simply multiply every term, so I get y of z minus 0.5 z to the minus 2y of z minus 0.25 z to the minus 1 y of z, that is equal to x of z plus 0.5 z to the minus 1 x of z. Now I just take the inverse z transforms, and remember that y of z's inverse z transform is yn, so I get yn minus 0.5, the z transform of z to the minus 2y of z, that's just a time shift. That is y of n minus 2. Minus, this is again just a time shift, 0.25 y of n minus 1. And also remember that the z transform of x of z is x of n, plus this is again just a time shift, but now of x instead of z. So that is 0.5 x of n minus 1. And the final step is, since I want to write my output as a function of everything else, I just take all the terms that are not yn to the other side. And that's how I get this equation that I wrote earlier. So as you can see from this discussion, design of filters basically involves two things. One is either we approximate the filters, and we haven't even come close to how do you do the approximation. We have just talked about generally how you do you will do approximation using what types of filters. You either approximate the filters using FIR filters. There is a systematic way of doing that. We'll cover that. Or you can approximate ideal filters using IIR filters, which have constant coefficient difference equation form, or equivalently whose z transform has this rational form. And we'll look at how do we design filters that approximate ideal filters in that setting. Now in both the cases, z transform is going to play an important role. And at the very least, a few concepts of z transforms are going to play a very important role. So it's important for us to revise some of those important concepts. And for that, we'll just start off with the definition of z transform. We'll go on to describing the implications of poles and zeros for filters design and so forth. So a brief review, and this is going to be really, really brief, of z transform. So if you are given a sequence Zn, we say that it has a z transform g of z, where z is a complex number. So z transform is described over this complex plane, which we sometimes call the z plane. And the definition of z transform is simply given by n from minus infinity to infinity, g of n, z to the minus n, where the z is a complex number. Now a z transform is, since it can be defined for different values of z, it not only involves the expression or the polynomial in z, it has something called the region of convergence, or ROC. And the ROC of the z transform, it is defined as the region of the complex plane for which the infinite sum converges. So equivalently, if g of z is less than infinity, right, for some z, then this means that that Z belongs to the region of convergence. Okay. Now, since we are taking the Z to be a complex number, so we'll write it in the polar form. So write Z as equal to R e to the j theta. So we have, this is our complex plane, and basically each point in this complex plane we are going to represent it as Z equal to R e to the j theta, which simply tells us R is the length of distance from the origin and theta is the angle from the origin, right? The usual polar form. Now, the Z transform, the region of convergence, if you do the analysis, it is all based upon basically just summing up this infinite series. So the region of convergence is simply determined by the absolute value. So if g of Z1 is less than infinity and Z2 has the same absolute value as Z1, in the complex plane, the same absolute value means that you are actually living on a circle, right? Because absolute value just tells you the length, you can be anywhere. So if you know that you converge for some Z1, and then you know another Z2 which has the same distance from the origin, then g of Z2 will also be less than infinity. In other words, what it means is that region of convergence only depends upon the mod of Z. It only depends upon how far away you are from the origin. It does not depend upon where you live on the circle around the origin. So if you have this circle of radius r, if you converge on any one point on this circle, you converge for all the other points on this circle. So region of convergence is always defined in terms of the absolute value. Okay, so we only say it depends upon absolute value of Z, for which g of Z is less than infinity. Okay. Now, you must have also seen that region of convergence, because of this property, is always an annulus region in the Z plane. And it is always connected. So there are only three different types of region of convergence that you obtain. You either will have that your Z transform converges for all Z outside this circle. Okay, that is one type of region of convergence. This circle boundary may or may not be included. That's one type of region of convergence that you get. Another type you get is that your Z transform converges for everything inside this circle. And the last type you get is that you have this region that it converges between these two circles. Okay. Again, we are not going to go through the properties of Z transform in detail, but the region of convergence cannot be a disconnected set. Right? So something like this, you can't have a region of convergence like this. That you have this, and then you say that I have another region of convergence here. Okay. Why? Because it's disconnected. So this is not a valid region of convergence. Okay. So all of these things you have seen before.